okay, now we have in some ways a proof that these clocks are responsive and they will be responsive and hopefully can transform the work in future and can be used in clinical trial and clinical settings.
And what your studies help us to do is to get what I like to call a new dialogue with our bodies, where there's short feedback loops between, you don't have to wait 20 years for somebody to die to figure out, which intervention works best for them, right?
Yeah.
You can use these biomarkers of aging proactively that way, in an objective way, to compare multiple interventions for the same individual. And given, again, that 3/4 of us these days are dying from heart disease and cancer and diabetes and other things that are absolutely a function of interventions we might take or not take, such as exercise and diet, figuring out which ones are right for which people is absolutely critical. So my hat's off to you. I'm super excited about all this. Welcome back to the Human Life Expectancy channel. Today, we're joined again by Raghav Sehgal, faculty and director of the Longevity Clinic at Yale University. In our last video, we discussed his upcoming study on increasing the reliability of biological age estimates, making them even more appropriate for tracking the unique health of each individual. Please check out that video for a broader introduction to Raghav, aging biomarkers, and the many important findings of that study. Also, please refer to our book on more background for how insurers are using epigenetic tests to help policyholders live longer, healthier lives. Today, we're here to discuss another pre-published study called DNA Methylation Aging Biomarkers Are Responsive: Insights from 51 Longevity Interventional Studies in Humans, that Raghav completed with Daniel Boras, Albert Higgins-Chen, and other prominent epigenetic scientists. If you're interested in the future of personalized longevity science, please do us a favor and press like and subscribe to the Human Life Expectancy channel. Raghav, welcome back.
Thank you for having me, Tom. It's great to be here back again.
Great to see you again. And to start us off, can you please tell us what motivated this study?
Yeah, so just like the reliability study, we wanted to sort of go beyond proving the fact that the epigenetic clocks and epigenetic biomarkers are prognostic, right? So if we want to translate them into clinical settings, we need to show that they are sort of working for interventions, that they respond to interventions. And also, this is kind of a chicken and egg problem, right? If we don't quite know which is a longevity intervention right now, right? There are putative longevity interventions. There's so many interventions that could be potentially longevity interventions. So what we did was we took data from a lot of potential longevity interventions that are out there, right? People have said that these are longevity interventions based on mice studies, based on observational data in humans. And we compiled all of this data and said, okay, if we have all of this data, and if these epigenetic biomarkers respond to these interventions across the board, right, then we can say that a epigenetic biomarker is responsive, right, to these interventions, to longevity interventions, and we can move them to clinical settings. And that was the whole hypothesis of this study.
That sounds great. So, I've long said that what epigenetic science really needs now is more and better longitudinal studies of aging interventions to see which work best for which people. And so if I understand correctly, well, this isn't an additional study of looking at other people, but rather it's looking at 51 prominent longitudinal studies that have already been done so far and comparing them on an apples-to-apples basis so that we can really get the maximum learnings from them in answering the important questions of which biomarker clocks work best and which interventions work best. Is that roughly right?
Yeah, so many of these, what's really interesting is some of these studies had already been done. Many of these studies were publicly available studies, right? On which these DNA methylation clocks had never been calculated, as well as many of these studies were behind sort of closed doors. So DNA methylation data had been generated for these studies by sort of these researchers, but never quite ever shared publicly. So what we did was a really large exercise on not generating this data, but making this data publicly available and harmonizing it. Sort of collecting and curating this data and putting it all together and harmonizing it, and then calculating all of these epigenetic clocks and biomarkers on top of them.
Got it. So you're talking about the TranslAGE database you put together, correct? TranslAGE-Response?
That's absolutely correct, Tom. Which was the whole part of this effort, which is harmonizing all of this data, which is putting all together these clocks and calculating them. And there are about 100 different biomarkers that we calculated in this TranslAGE responsiveness arm, and putting all together these data sets. And even though in this study we use about 51, the TranslAGE responsiveness arm has now about over 100 different data sets that we have made publicly available for use for researchers that are out there.
That is so important for the advancement of the science. It's great that exists. And so, again, just to be clear, so many different studies have done, but for example, some of them might use PhenoAge. Some of them might use GrimAge 1. One might use GrimAge 2. Another one might use Dunedin age, right? Or Dunedin pace is what I meant to say. And so putting them all on an even apples-to-apples basis is important for figuring out which of these measures work best for which interventions, and ultimately which interventions work best. So for our listeners, could you please explain what surrogate endpoints are and why they're so important?
Yeah, that's a great question. So clinical surrogate endpoints are essentially a proxy in a clinical trial. So think about it this way. If we were to run a clinical trial for aging right now, that clinical trial would essentially run for 20 to 25 years. So let's take an example right now. If you were to give a drug to an individual who's 60 years right now, their average length of life of an American is about 80, 85 years of age. So you would have essentially wait till they die, right? To see if
so you'd have to wait 25 years before you get insights. And that would be very slow.
That would be very, very slow. And a lot of money, right? A lot of money spent, right?
And a lot of people dying and suffering from disease that might not need to in the meantime.
Yes. Exactly, right?
Okay.
And so what you need is a proxy, right? That can tell you whether this drug is working or not, right? So what that proxy needs to do is two things. It needs to predict mortality and disease really well, right? That this particular proxy needs to tell you that this proxy is mortality being increased or decreased by this particular intervention, by this particular thing, and this this proxy needs to predict mortality altogether, or the count of diseases or health span as we call it. And the second thing this proxy needs to do is respond to this intervention, right? It needs to be responsive, right? I would additionally add, if this proxy needs to be used in a clinical trial, it also needs to be reliable, right? It shouldn't fluctuate too much, right? So it needs to have 3 dimensions: prognostic, responsive, and reliable.
And that's what your studies have been focusing on.
Absolutely. And in some ways, this proxies, and this is what I would say is a clinical surrogate endpoint, right? A surrogate endpoint needs to be prognostic, responsive, and when it is a prognostic and responsive biomarker, right, that can be used in a clinical trial, right, instead of the actual outcome, right? That is what I would say is a proxy, ideal surrogate endpoint.
Instead of waiting 25 years for the end point of our lives, we have these surrogate endpoints, which are these biomarkers, but you got to make sure they're the right biomarkers, right?
Right, absolutely.
And that's what these studies are all about. That makes perfect sense.
And we can take an example here. And I know we're already on time here. We can take an example here. We take, for example, a really good example of this is in the 1950s and 60s. Before 1950s, 60s, we did not have a surrogate biomarker for heart disease, right? Till what we call the Framingham Heart Study happened, right?
Yep.
So there was a thing called the Framingham Heart Study, which actually happened about 2 hours away from where I live. I live in Connecticut. So 2 hours away from this place is the town called Framingham, where this Framingham Heart Study happened, right? About the whole town, and their whole data was collected, and a bunch of things like blood pressure and cholesterol and all of these metrics were collected. And they essentially said that we'll figure out the metric that predicts heart disease, right?
Mm-hmm.
And they figured out, of course, they had some predisposed knowledge that it might be cholesterol, right? They'd done some previous analysis, but then they proved that it is cholesterol. And then they also showed that it responds to interventions like exercise, right? In that study.
Mm-hmm.
And that's how they showed that cholesterol is that proxy biomarker. But then that later essentially allowed to be used for cholesterol to be used in trials for statins, right?
Yeah.
And that is why we now have statins as one of the best drugs that is out there, right? To lower cholesterols and therefore prevent heart disease. Yeah. And so statins is a blockbuster medication that is built on the idea, right, that it can lower cholesterol, which is a risk, which is a proxy for heart disease, right? And that's it.
Thank you. So this surrogate endpoint stuff is not some esoteric PhD level stuff that doesn't matter. This is very blood and guts visceral. Do we know what we're doing? And have we found something that allows us to greatly increase the pace of our learning in helping people live longer, healthier lives?
Absolutely.
Great. So let's move on to kind of responsiveness across interventions. Your work finds that clocks trained to predict mortality or pace of aging show the strongest responses across interventions. Could you unpack a little more of why these clocks might be more responsive compared to others?
Yeah, and actually I would probably add to that. It's not just sort of the clocks that are mortality or pace of aging predictors, it's the reliable versions of those clocks. So if you had just simply sort of Dunedin pace of aging clock, that wouldn't be responsive. The pace clock, which is the reliable version, so the second version of that clock, which was based on sort of the reliable CPGs, that is the version that is responsive. And part of that is because there is a complex combination of two things that we believe that is happening. One is that these, and we talk about this towards the end of the paper, not so much in the start of the paper. There's the hypothesis, we don't really talk about that, but we talk more about the data analysis. The first generation of clocks typically capture is what we call is the ticking of the biological epigenome, right? We call this the stochastic component, right, of aging, right? While the second and the third generation clocks capture the non-stochastic component, which is what I call sort of the mortality clocks, or the pace of aging clocks capture what I call the more biological processes of aging, right? So the stochastic component is just like a ticker, right? It will keep on adding up, right, as you age. This is a lot less modifiable, right? This is what the generation 1 clocks are capturing. The biological processes that are being captured, though, by the mortality and the pace of aging clocks, on the other hand, those, on the other hand, are a lot more modifiable. Those are the actual biological processes, right? Those are the non-stochastic.
And when you say modifiable, you mean modifiable through intervention?
Through interventions, absolutely. Yes.
Okay.
And more importantly, so that's the aspect of them being modifiable through interventions. But then the second aspect is, how do we capture this information, right? From a mathematical perspective, from an algorithmic perspective. So that goes back to the point about our last podcast, right? The signal to noise ratios, right? If there is a lot of signal to noise in a clinical trial, right, you will not be able to capture it with a small sample size, right? And
you mean if there's a large signal to noise, you can capture it. If there's a small signal to noise, you cannot.
Yes.
Right?
Yeah. I said that wrong.
That's right.
My confusion. So essentially, the reliable clocks, what they are able to do really well is that they are able to capture this. They are more reliable in the sense that they have CPGs that have this high ratio of signal to noise, right? They're essentially capturing sort of these CPGs that have more either have more signal to noise, or they are capturing by using sort of PC's approaches. They're improving the signal to noise ratio, right? And by improving sort of removing all of the noise that is there, right? We require fewer samples. So even with fewer samples, you can get a more significant signal, significant p-value, right? And that is why we are able to see sort of changes very quickly or significance very quickly. And these clocks are becoming more responsive now in some ways. And so that sort of comes back to the point, like if you have a more reliable clock, this clock becomes more responsive. And that, at the end of the day, is the story here. That more reliable clocks are responsive.
Yep. Great. Well, then let's get into it. Which clocks demonstrated the highest response across the interventions you looked at?
So those were sort of 5 clocks that we saw. So we looked at sort of around 110 different biomarkers. Of those, where there were about sort of top 18 sort of clocks we looked at. These would range from generation 1, 2, 3, and onwards. And of those, 5 of these epigenetic clocks really sort of stood out to us as being the most responsive. These were PC GrimAge, GrimAge V2, PC PhenoAge, Systems Age, and Dunedin Pace. These were the 5 epigenetic clocks that were the most responsive. Now, I wouldn't say that one was more responsive than the other, right? Because they all sort of responded equally. But I would say that, for example, Dunedin Pace was responding a lot compared to others, right? In a lot of ways. Or PC GrimAge showed sort of the most amount of deviation in terms of sort of responsiveness in terms of effect size. So those 2 definitely stood out, but all 5 of them were responding to interventions across the board. And what is important to note was that all 5 of them, as compared to the other 18 that were other sort of 13 that we were looking at, all 5 of these were reliable clocks, and they were mortality and pace of aging clocks. So that was what was distinguishing them from the rest.
Thank you for that. Yeah, in reading it, I was also surprised to see the Dunedin Pace clock come out as well as it did. I think I remember that it never disagreed with the other clocks. It was the only biomarker that seemed to be changing unbiasedly in both healthy and diseased populations. There are some interesting aspects of that. And I think also another important aspect of it is it's actually not a biological age measure, right? It's a measure of the rate of aging.
Yep.
Can you talk a little bit about how its uniqueness might have made it more appropriate for reflecting interventions?
Yeah, I think it's a really interesting dimension to talk about, which is rate of aging metrics are almost a really beautiful metric, in my opinion, which can capture sort of clinical trial variation quite well. So the way I think about it is there is an upgrade from Gen 1 and Gen 2 that Gen 3 sort of these rate of aging metrics get, which is Gen 1 and Gen 2 are capturing what we call as cumulative damage, right? So what they're doing is they're looking at cumulatively how much damage has happened over a lifetime, right? That is what chronological age is doing, right? How much damage has happened till now, or what is a mortality clock doing? How much damage will happen in the future? That is what it's trying to predict, right? So it's cumulative amount of damage. But what a rate of aging clock is doing is, if you think about an hourglass, right? So if you think about it, how much sand is left at the top versus how much sand is left at the bottom. A rate of aging clock is trying to figure out how much sand is slipping through. What is the rate of the sand that is falling through? Now that is very dynamic, and that switches very quickly, right? And so you can see changes in that very quickly, right? And that is perfect from a clinical trial perspective, right? If you're thinking about to see response, right, of an intervention, that is really good. If you want to see that if something has changed, if something has changed, how quickly the sand is moving through that hourglass, if the sand was earlier moving really slowly and now it's moving really fast, versus if the sand was moving really fast and now it's moving really slowly, right? That is great if you think about it, right?
It is. It's a great metaphor. Basically, it sounds like it's easier to pick up changes in the rate than it is changes in the total mass of sand that's in the bottom. Because there's more of it there, it's harder to look at. That's really interesting.
Yes, because the relative amount to look at it is really different. And I think that is why it's so powerful as a metric.
Very cool. So it makes sense that some clocks might be better suited for intervention tracking versus just estimating biological age.
Yep, absolutely.
Very, very cool. Very cool. All right. Well, let's move on then. Let's start talking about. Well, actually, hold this. Before we focus on the interventions that did the best job of helping people live longer, healthier lives, how did you determine whether interventions were effective? Can you tell us about the 2 rules that you used to determine bona fide effects?
Yeah, so the interventions were effective or not, we did a very sort of quick, what we were trying to attempt to do here was a very quick analysis to see whether we curated a database of interventions that were longevity interventions or not. So as I started off by saying, this is a chicken and egg problem, right? We do not know which interventions are longevity interventions, right? So we have a problem here. So what we need to do is we need to have an idea generally stating that in general, we have a database of longevity interventions. And how do we say that we have a database of longevity interventions? If in general, we have a database of interventions which have more than 50% are decreasing epigenetic age, and a majority of them, or a major chunk of them, are decreasing epigenetic age, and over a certain amount of them are decreasing sort of epigenetic age significantly, right? And so what's the best measure to do that? We use the very well-known clocks. And at this point, we don't know which clock is responsive, right? We average out those clocks and we say, okay, are these clocks in general decreasing epigenetic age for these interventions or not, right? And so for each intervention, we look at that effect size and we see for about 63% of the interventions, epigenetic age decreases. For 37% of it, they decrease significantly. Only about sort of 7% of them, there is an increase significantly, right? So 37% decrease significantly, 7% increase significantly, right? So in general, we have curated a longevity interventions database, right? And so we can make the argument now that if we were to do a test now on all of these interventions, right? And say, is this an interventional database? Is this a clock that is responding across these interventions, right? It should, right? Across 37% of these interventions, right? We can say, yes, a clock should respond across all of these 51 interventions. And that is what the hypothesis was.
Got it. So you looked at interventions and made sure that they modified DNA biomarkers of a given generation to the same magnitude and roughly in the same direction. And then so the idea the idea there is that we don't with the interventions themselves, right? We don't want to go. We don't have a lot of replicate studies, right? We only have some, to some extent, right? And we have some hypothesis around, okay, this is great. We have like 2 Mediterranean diet studies and we have like 2 anti-TNF studies. And in those cases, we can make estimates around like, yes, in general, if the directionality is the same for a lot of these clocks, if the directionality for a lot of the same generation of the clocks is same, then the intervention is probably giving the right result, right? But beyond that, we don't want to make sort of broad or overarching claims and saying like that these interventions are the ones that are generally working. We do make some claims around that in the future, if you want to say that if an intervention is working,
you may have like at least 2 or 3 studies showing the same results like this. And we give examples of that as potential rules to move by in the future.
Yeah. Well, I hope you'll forgive me. I mean, in reading the paper, I couldn't help but be seduced, if you will, by looking at the impacts of the various interventions. And I think the question on a lot of our listeners' minds is, well, okay, which interventions worked and which one did you find? But I think what you're saying is that actually wasn't the central thrust of your study. The central thrust of your study was just proving that these various interventions were responsive.
Yep.
Right?
Yep. I think that's kind of the central thrust here, that these various interventions are responsive. And to some extent, right, to really run this, to really give a succinct answer and say an intervention works, right, we need to run a trial, right? And these are, at best, these are small retrospective trial data that we are reanalyzing, right? To actually give you the answer that an intervention works, I will need to actually take a biomarker from this set, right, and use it as a clinical endpoint in a trial in the future, and then essentially say, yes, that intervention works, which is probably what is going to happen in something like ARPA-H PROSPER trial, right? That is what is going to happen in the PROSPER trials in the future. But that is not,
and of course, in the trials that we're wanting to do with insurers, it's the same sort of thing. People go on different interventions, whether it's diet, whether it's exercise, et cetera.
Yes.
And then you can see, well, do these interventions actually have an impact on biological age or the pace of their aging? Absolutely, yes. Well, that being said, I couldn't help but notice that, I mean, it was nice to at least see that many of the interventions had the impact that we thought they would.
Yes.
Smoking hurt longevity, diet helped longevity, metformin had a strong positive response, and there were many things that were exactly as expected. Can you tell us more about kind of the findings of that part of the study, of the different interventions?
Yeah, in general, I think it agreed very much with what we saw. We saw, for example, when we sort of agglomerated the interventional effects, we saw that lifestyle interventions were generally sort of decreasing, pharmacological interventions were generally decreasing, like all categories of interventions were generally decreasing epigenetic age, lifestyle, pharmacological, supplements, and medical procedures. Lifestyle and pharmacologicals had the strongest effect, with them being more significant, supplement and medical procedures not as much, but nevertheless, they were trending downwards. And in general, I would argue that even though some interventions were a little more unexpected, I would say, for example, we saw that there were some trials that were sort of more shorter period that did not show as much of an effect. For example, an exercise trial, right, which was relatively shorter. That was, I think, an 8-week intervention period, right? So I would not have it was done in a PCOS population of women. So a very specific population. We did not see much of an effect in that case. But then in trials where there was a Mediterranean diet given plus exercise, we did see effects, right? So we had mixed results in certain cases, but in general, lifestyle interventions were decreasing epigenetic age. Or for example, another one was we saw that rapamycin did not specifically decrease epigenetic age, which has been touted
that surprised me.
Yeah, which has been touted as this thing. But that was interesting because that particular trial has actually shown that that particular trial has actually shown no effect in general. And that's not something that is that has been really well known for that particular trial, because there was the particular sort of use case in that trial, the drug use case that was used was a compounded drug. And so the bioabsorption might have been lower than that was expected in this case. And the other problem in that trial potentially could have been that even though the rapamycin even if the bioabsorption was high, it was in typically really healthy adults. So it could, if in a different population, it might have a very different effect. And so if we look at, but in general, again, pharmacologics, like others, had decreasing effects, right? Like metformin.
I was
stuff
really
like that.
interested in that. The anti-TNF therapies, again, for our listeners, anti-TNF drugs block inflammation and generally do have a strong positive response. But it kind of raised a question for me. How much do short-term pharmacologic impacts on DNA methylation clocks actually correlate to health and mortality endpoints?
Yeah. So what we also did was, and again, this data around supplementary is not available. We regressed out all sort of cell proportion information from all of these clocks, and these changes still remained. So essentially the clocks were still responsive, and all of these effect sizes still remain, which goes back to the point that if you took out all of these sort of inflammatory sort of changes that might be happening, right, which would be leading to immune cell changes, right, which are often associated with clock related changes, these changes still maintain, right, or these effects still maintain. And I believe that I again still believe that immune cell variation still should be incorporated, but to sort of calm the nerves of the people who believe that immune cell variations are maybe driving these effects, we removed those effects, but and still saw that these changes are maintained and the clocks are still responsive.
Got it. Another thing that surprised me was that in general, interventions that involved exercise didn't have as large of a beneficial effect as I think most people believe they genuinely do. I mean, your mentor, Morgan Levine, put out a video recently saying that exercise is the #1 antidote to aging. And many would agree with that. But I didn't see that jumping out of the study as a result here. Do you have a sense for why?
I don't agree or disagree with anyone there, I would say. I think the data is the data on what we have, which is that what I saw with the clinical trial data is this is what we got, right? And I do not disagree that exercise helps at all, right? Exercise is a great way to sort of improve health, right? It improves cardiovascular health. It improves a bunch of different outcomes. In the data that we had, right, this is what we read, right? Now, is this a function of the clinical trial data we had? I'm not sure. Is it a function that a different exercise clinical trial data will show a better outcome? I don't know that, right? Is it a function of the epigenetic clocks, right? Maybe a better, more responsive, more reliable clock will show an even stronger response. I don't know that, right? But I can give you an answer to the data that we have here, and the data shows what it shows.
Yep, that makes sense. And so, independent of what someone might expect, this study absolutely advances our knowledge by just saying, here is the fact, right?
Yeah.
Well, when we did this work across all these longitudinal studies of longevity interventions, we found that here's what the impacts were. And I think it's also fair to say that epigenetics is an evolving science. And we're learning more and more about these biomarkers. And what we're advancing here is by saying many, many biomarkers are absolutely responsive to intervention. That's the main thing. And this study was neither designed to, nor does it kind of stake its reputation on the specific efficacy of individual interventions. That's not what this was about. Yeah,
which is exactly the point why we took 51 interventions, right? If this was a study that said we looked at lifestyle interventions only, or if we looked at exercise, that would have been the study that we would have gone for, right? Instead, we looked at 51 interventions across the board, from lifestyle to supplements to medical procedures to pharmacologics, because we believe we do not know the answer of which is a good longevity intervention, right?
Yep.
And that's kind of the approach that we took, that we do not know the answer. All of the people are right. We believe so, right? Okay. All people are right.
Let's look at the data.
But let's look at the data, right? And this is what the data tells us right now. And we believe that all 51 of these interventions could be putative longevity interventions, right? And our question is, if they are all putative longevity interventions, then the biomarkers should respond to them.
Yep, that makes sense.
And
you
if the
discovered other things.
biomarkers are,
go ahead, please.
Yeah, if the biomarkers are responding to them, right, then they are responsive. And that's what we wanted to show.
Yep. You showed other things too, though. You talked a little bit before about how longer interventions tend to have more impact on aging rather than shorter ones. Is that right?
Yep. Yeah, so that is a really interesting insight, because I think we do sort of nudge towards this idea that longer term interventions do tend to have potentially or longer interventional periods do tend to have a better effect size. I think it goes back to the idea that you have a better signal, essentially, right? Which you can essentially disentangle from just a mathematical perspective, and which is what which the clocks are essentially able to better capture. There's less noise, which the clocks are essentially better able to disentangle.
Yep. And intuitively, it makes sense that running a mile every day for a year is probably better for you than running every day for 3 days.
Absolutely.
Right. You also looked at the impacts on unhealthy people versus healthy people. Can you tell us about that? I thought that was really interesting.
Yeah, so that was the idea was we wanted to think about this from a perspective of when we're going to run these trials in humans, right? And as we think about running these trials in humans, the population that we choose is going to matter a lot, right? Of how these biomarkers are going to be responsive, right? And so our question was that what is the right population to start with, right? Or where do these biomarkers work the best right now, right? And what we were able to show was at least they work really well in what we call as typically populations that have some kind of disease or are predisposed to some kind of disease, right? Or what I would call as accelerated aging populations, right? But populations that do not have significantly accelerated ages, right? Or as I would call them as healthy aging populations, we have a tougher time showing response, right? Now, this is an important problem, so to speak, right? Or to address for the field, because as we move towards running clinical trials and using these biomarkers in healthier populations, we need to think about this problem more, because right now, for example, we're thinking about doing GLP-1s hypothetically, right, in individuals with obesity, which we can say are GLP-1s are great for individuals with obesity. We might be able to say GLP-1s is I'm just giving an example here, is a pro-longevity drug in people's with obesity. And we might be able to even run an epigenetic test and show that, right? But when we start running this in healthy people, I think that might be a bigger challenge, because we might not be able to show that responsiveness very easily, because people aren't already accelerated in aging, and showing that change might become a lot more difficult for those epigenetic clocks at the present generation of those clocks. So we might need even more sensitive clocks to show that change.
This is a really important issue, I mean, for us as well. I mean, as we think about insurance populations, those are generally more healthy people, right?
Yep.
And the intuition that occurs to me, let me know if this is wrong, but the intuition is something like, well, heck, when you're really thirsty, water's going to help you more than when you're not, right?
Yep, exactly.
And so if you're aging very poorly right now, any intervention is going to help you more than the same intervention when you are already aging well.
Absolutely.
I mean, seems to make sense. And so, yeah, there's plenty more to do here, but I thought that was a really interesting thing that your study teased out. If we zoom out, let me change a little bit here and talk about, enabling precision health. If we zoom out, one implication of your work is that epigenetic tests don't just tell us whether an intervention works on average, they can potentially reveal who it works for.
Mm-hmm.
And many insurers and employers are interested in motivating people and moving beyond generic wellness programs toward precision health, understanding again which specific interventions actually improve outcomes for specific people. And putting your two studies together, one of them minimizing the short-term biological variability in clocks, and this one now showing the intervention responsiveness, what can we say about epigenetic aging markers' unique abilities to support that shift?
No, I think what I'm seeing is that on one end, we're seeing that clocks are responsive, right? We're seeing biomarkers are responsive. On the other end, we're seeing that there is a small problem around them being a little sort of variations in short-term reliability, but we can fix that problem, right? Mm-hmm. And so once we are able to sort of build this ecosystem of clocks that are responsive in the longer term, right? And are sort of unresponsive to short-term variations, right? We can then really start stratifying people, right? To saying like, hey, who's going to respond to what intervention, right? If a person is responding better to this intervention in a short frame of time very quickly or not, right? Maybe over 2 weeks, 4 weeks of time, right? And then say, this person lies in this particular stratification of an individual who responds to this type of an intervention, and they may benefit from this, right? And of course, these clocks come with the benefit of identifying which individual is accelerated in which dimension of aging, right? So our previous work in systems age has already shown you can identify organ-specific aging, right? Using just whole blood DNA methylation. So you can specify, this individual has a really high heart aging, but a really low liver aging, right? So now you can think about it. You can really leverage, this individual has really high heart aging. They should probably be given sort of specific interventions for their cardiovascular age. And now they need to sort of give those interventions in this particular dimension to slow it down. And these are the particular interventions that work. And the best part of this is these will be reliable and are highly responsive and can be very, very customized.
That's why I love these two studies you've done so much, and why I'm so delighted to have videos on both of them. It seems so obvious to me that they're two parts of the same thing. The reliability from the first study, together with the responsiveness from the second study, really gives us the actionability, right? The ability to use these biomarkers to identify which interventions work best for which people. So I recognize them both as big, big advances, and salute you and your teams for the great work that you've done on them.
Thank you so much, Tom. Thank you.
What we're needing to do, and what your studies help us to do, is to get what I like to call a new dialogue with our bodies, where there's short feedback loops between, you don't have to wait 20 years for somebody to die to figure out, which intervention works best for them, right?
Yeah.
You can use these biomarkers of aging proactively that way, in an objective way, to compare multiple interventions for the same individual. And given, again, that 3/4 of us these days are dying from heart disease and cancer and diabetes and other things that are absolutely a function of interventions we might take or not take, such as exercise and diet, figuring out which ones are right for which people is absolutely critical. So my hat's off to you. I'm super excited about all this. I had mentioned that insurers and employers are interested in this type of study, and we're, of course, interested in it at Human Life Expectancy, Inc. Who else has shown interest in these studies?
Yeah, so of course, clinical trialists are really excited about this study, right? So people who are interested in doing clinical trials for aging are really excited about the study. People who are in the longevity ecosystem in general are really excited about this. I know Brian Johnson tweeted the study quite extensively, and that got a lot of likes and tweets or whatever. it's called it now on Twitter/X. And then I think David Sinclair tweeted about this and talking about the interventional effects and all, which got a lot of attraction. And so it's I think in general, the impact of this study has been very far and wide reaching, which is from people in just the longevity ecosystem to academic researchers who are thinking about these biomarkers, to sort of companies, right? So companies, sort of pharmaceutical companies who are thinking about running early stage startups in the aging ecosystem, who are thinking about running these clinical trials in aging and thinking about epigenetic biomarkers as readouts, have come and talked to me about this and seen what biomarkers should we use, why should we use them, in this context. And so I really feel that this is a study that is really transformative for the field, to say that, okay, now we have in some ways a proof that these clocks are responsive, and they will be responsive, and hopefully can transform the work in future, and can be used in clinical trial and clinical settings for people and humans.
Absolutely. That's fantastic. And, have you, I'm sure you have, what do you think we've learned from this study that might help us in the implementation of real world programs, such as those in insurers or those that your fellow doctors are looking at in studies, to take full advantage of epigenetic responsiveness?
Yeah, so one thing is that there's definitely some biomarkers that are better than others, right? That we need to move past what I call as sort of the Gen 1 clocks, right? The Gen 1 clocks are amazing, right? They are inspirational clocks. They are what defined the field, right? And they have a very specific use case. They are still used in very specific settings, right? They're very useful in very specific settings. But if we need to think about them from a clinical standpoint, I think we need to move past them, right? We need to move past into what we call as the second generation, third generation reliable clocks, right? I don't call them third generation, by the way. I call them 2+ right now, right? That's what I call them in the paper, the mortality and the pace of aging clocks. And the reliable clocks, the reliable versions, are the ones that I'm really excited about. Those are the ones that I believe are the future forward, that would be really sort of putting responsiveness on the map, because those are the ones that would be really allowing for responsiveness of interventions the most. And so overall, to speak, that's one takeaway I would tell a lot of physicians, that if you're thinking about implementing interventions for your patients, choose the right biomarker. And that right biomarker is not going to be the biomarker that has the most literature right now about it, because that's probably the one that is the most. Which would be
like the Horvath or the Hannum, the early ones.
That's the one that is the most literature out there, right? It's probably the one that was published the first. It's probably going to be the one that is the newest, right? The most updated. So you might have to do a bit of literature digging, right? So talk to folks who are experts in the field, and talk to those folks so that you get a sense of like, hey, what is the newest thing? What can we learn? And how do we go from there, right? And they will guide you.
Thank you very much. Thank you very much. Raghav, is there anything else you've wanted to say that I haven't found a way to ask you?
Well, all I would say, thank you, Tom. Thank you for always being such a support and always sort of pushing forward the science of scientists like me. It's always amazing to come on here and talk to you about the amazing science we're doing. So thank you for bringing us on here.
Very kind of you to say. Raghav, thank you so much for joining us. Your work offers a real path to identifying which interventions work best for which people, and ushering in an era of precision medicine that we all are working toward. So again, super exciting stuff. Can't thank you enough for being with us. One other thing, where can people follow your research?
Yeah, so I'm available on LinkedIn as Raghav Sehgal Yale, Raghav-Sehgal-Yale, and also on Twitter as RV_Sehgal. You can also reach out on my website, raghav-sehgal.com. I think, and my email, raghav.sehgal@yale.edu. That's about it.
Thank you very much. I'll make sure to put that in the notes for the video.
Yeah.
Thanks
Cool.
again, Raghav.
Thanks, Tom.